Thank you. And thank you, Fernando, for the invitation. It's a pleasure to be here. So I'll talk about sweep-out inequalities in geometry. So first I will go over some previous results, and then I will present a new result and maybe and sketch the proof of it. Okay. At least in a special case. So what do I mean by sweep-out inequalities? Here's an example where say you start with a convex body. So see, it's a convex body in Rn plus 1. You just look at the boundary of this convex body. So it's a sphere. It's an end sphere. And let me draw a picture. Yeah, so here. So I have this sphere in Rn plus 1. And then what I do is I fix a plane here, let's say a k plus 1 dimensional plane, and then I'll look at all the planes which are parallel to P0. Okay, so I get all those planes, P parallel to P0, and then I look at the intersection between P and the sphere. Okay, so I get a kind of slices like that. And so the dimension here is K. And what I want to do is I'm going to look at the volume, the k-dimensional volume of the intersection of P of one of these planes with a sphere. Okay. And what I do is that I take the supremum of this volume, okay, in that direction. So take the supremum of P parallel to P0 here. And then I want, so here I'm gonna get like sort of a thick part there. And then I want to minimize that over all directions P0. Okay. So here it's a k plus 1 plane. Okay. And this I call that, let's say, I'll call that LW. Well, you put it there. LWK of S. Okay, for the sphere. So this is, so LW for linear width or linear K width. And what we want to do is compare the linear width with the volume, the n-dimensional volume of the sphere. And we have this result by Treyberg's, I think it's in 85, that says that let's see how I'm going to put it. I'm going to put it like that. So the linear width is bounded from above in terms of the volume of S. And here you have to put the right power, so that's k-dimensional. So here you have to put k over n, okay, to have the right power. Okay.
This is a multi-parameter sweepout.
I'm sorry?
It's a multi-parameter sweepout, right?
It's
What do you mean parallel?
you have to fix a direction, and then you look at all the planes which are parallel like that. So you take the maximum, and you kind of minimize this maximum. So
It's like high dimensional.
yeah.
Okay.
Yes.
But it's not. Is it one parameter or multiple?
Oh, Well, it's multiple parameter because P0 describes all the Riemannian.
That's right.
Yeah. Okay. Yeah. Okay. And of course, I mean, this result relies on the Euclidean structure of the invariant space. Okay. And so we want to do in geometry, in Riemannian geometry, just try to deal with abstract manifolds, abstract Riemannian manifolds. So here now, okay. So that's an example of what I mean by a sweepout inequality. But now let's say that now M is a closed Riemannian manifold. Let's assume it's orientable. Closed orientable Riemannian manifold. Riemannian manifold, N manifold, and so now we want to define the width of it, and that one way to do it. Let's say here it is n minus 1, so we'll be dealing with a sort of hypersurfaces. One way to do it is to look at. So you're going to look at a Morse function, and so we have this picture. That's our manifold, and you look at so that's R, and you look at the level sets. Okay, so you see, it can be disconnected. And so you look at the level sets, and what you want to do is so you define the n-1 width of M kind of the same way. So you look at the level sets, you take the volume, so the n-1 dimensional volume. Well, let's see. And you want to take the supremum over T, and then you take the infimum over all Morse functions. Okay, so that's one way to define n-1 width on Riemannian manifolds. Okay, and of course we want to compare that with the volume, like before. So let's say, so in the, okay, so again it's versus volume. So in the case of surfaces, so let's say n equals 2. So we have this result from Balachef. It's maybe, I don't know, I don't remember, maybe 10 years ago, something like that. So let's say that M is a genus G surface, and we proved, let's put it that way, so here, so n is 2, so it'd be like the one-dimensional width, something like that, of M is bounded, so it should be something like, I don't remember the constant here, it's a universal constant, and here it's something like that, okay? And that's true for any metric on M, and there should be a square root here, right? Okay, so it's sort of a similar result. I mean, here the constant, so that's sort of the constant. The constant here depends on the, which was there. The constant here depends on the genus but it has to. I mean, it's roughly optimal. Roughly optimal in the genus. I'll talk maybe about that later. Okay, we cannot have something like that. Cannot get rid of the genus here. Okay. All right. Okay, so that's for the two-dimensional case. So that means, yeah. So that means if you have like a surface with small area, you'll be able to sweep out with one cycles, with the short one cycles. Okay. So now, what about in a higher dimension? So here, of course, what we want to do is get something like, the question is, do we have this inequality there? So the volume, and here the right power should be n minus 1 over n. Okay, so that's the question. And you see that it's, when you think about it, you see that it's related to the, oh, let me erase this. It's related to the Cheeger constant. Okay, so the Cheeger constant, let me remind you, definition, it's, so you have your manifold, and then you split your manifold into two parts, D1 and D2. Okay, so you have your manifold and you split it like that, D1 and D2. And then you take the volume of the boundary of your domain, any of them, because they have the same boundary. And then you divide that by the volume of the smallest part. Okay, and then you see that in order to have such a bound, you need an upper bound on the Cheeger constant. Okay, and why is that? It's because, okay, say you have a sweep out. All right, so here, say you have a sweep out. Oh no, say you have a sweep out. So at some point your sweep out is going to, by hypersurfaces. At some point the sweep out is going to split your manifold. Is it what I want to say? Hold a second. Yeah. At some point, yeah, your sweep out is going to split your manifold into two parts with the same volume. Okay? And that's be at some point, so that'd be, I think I called it H. Yeah? So it's split it like that, and of course the width will be greater or equal than the, so you sort of take the h here, that sort of, which is close to the infimum, so you have this h, and then you look at the time where it splits the manifold into two parts of equal volume, and at that point the width is precisely greater or equal than the volume of this slice there. Okay, but this, which is there, should be okay. So you have also this bound because of Tier constant. So so the volume here is 1/2 of the volume of the manifold times you have this lower bound times the Tier constant. Okay, and you see that. So what you want is that kind of. What you see that you need that kind of upper bound on the Tier constant. You need something like that. Because if you don't have this, then you see that you get here the volume would be the volume. Yeah, so you replace this. I mean, if you don't have this upper bound, then that means that you have another lower bound there, and that would give you n-1 over this. Okay, so it's very different from that. Okay, so we need an upper bound on the Tier constant. Okay, and actually there are examples here where we don't have this upper bound. Okay, so there are sort of counterexample by Burago and Ivanov on the torus, and I think there's also a result by Papazoglou and Svensson for any manifold mention at least 3, I think, or something like that, or maybe on the sphere. But it's so in general you don't have this upper bound, and therefore you don't have this Sweepout inequality. Oops. So we need some restrictions on the metric in order to ensure that this upper bound is satisfied. And one way to do that is, because we have this theorem, is to consider the Ricci curvature. So we have this theorem, which is due to Korevar. There are also some kind of other proofs by Grigorian, Netruzov, and Yao, as well as Colbois, Martin. I'm mentioning those names because later on in the proof I'm rather use their techniques developed by these two authors. So here, so you have M, which is let's say a closed Riemannian manifold with non-negative Ricci curvature. Well, then what you have is that the entropy, you precisely have the entropy, an upper bound on the entropy, exactly what you want. Okay? So then it makes sense to consider metric satisfying this lower bound on the Ricci curvature. So it won't be a curvature-free estimate anymore, as was the case on surfaces, but I mean, the truth is that we can expect such a curvature-free estimate. So, and so then, just want to mention this result, which was obtained independently by Glyn AD and Jokumovic. and myself. So here we consider a complete Riemannian manifold with non-negative Ricci curvature. Okay. And then what we have is that for every bounded domain G in M, so the width, the n-1 dimensional width, is bounded from above by the volume. Well, it's a G. And the right power is n-1 over n. Okay. So in that case, we have the desired inequality. Okay. Then there's actually an interesting corollary of these results that, okay, say now that M is closed and you take for the domain the whole manifold. Okay, so here would be sort of the width of the manifold and then the volume of the manifold, not just the domain. And we know that, so here if we use Almgren-Pitts theory, and more precisely resolved by Pitts and also Schoen and Simon, yeah. So that using Almgren-Pitts theory, but we can show that there exists on such a manifold, on the closed manifold with non-negative Ricci curvature, there always exists a closed embedded minimal hypersurface with S. Well, I should say with as always, with a single set of Hausdorff dimension at most n-8. Okay, so there exists a closed embedded minimal hypersurface whose volume is bounded from above by the volume of your manifold, like that, with this power. So that means that if you have a manifold with non-negative Ricci curvature, and that the volume of this manifold is very small, you can always find a closed embedded minimal hypersurface in it, or of small volume. Okay. All right. Maybe I can just sketch the proof and then I want to talk about something else really, but let me just sketch the proof just to give you the flavor. Okay, so here's the sketch. So you look at the Cheeger constant, of course, yeah, which is over there. Oh, maybe I can just use that. Yeah. So we know that under the curvature assumption that we have this upper bound, and let's say so say here you have so you get a splitting that sort of realized almost the Cheeger's constant. So you get so here you have D1 and D2, d2, and then assume that d1 and d2 have almost the same volume. So that means that I don't know, the volume of di is not too big, just like that, and not too small. Okay. So what we get here is that so we have this hypersurface, okay, this one S, and we know that the volume of S is, okay, so here, so the volume of these two quantities is roughly the volume of M. So what you get is you get precisely something like that. Okay, so it would be 4/3 of the volume. I forgot the Cn. The volume to the and the right power is n minus 1 over n. Okay, so that's good. And then we repeatedly apply this construction, okay, with this domain and this one, and okay, and if we're lucky, but we're not, if we're lucky, so here we would cut it with a hypersurface satisfying the same inequality. Actually, with say here, if I consider D2, here you replace the volume of M with the volume of D2, which of course is less than the volume of M, and that goes in the right direction. So if we're lucky, those hypersurfaces, so and we keep applying this process, you know, and if we're lucky, all those hypersurfaces remain disjoint. Okay, doesn't happen, but they remain disjoint, and so here you see that we get a kind of a discrete version of our theorem. Okay, so we get like a bunch of hypersurfaces whose volume is bounded from above by this quantity, by the volume of M, and then you kind of, if you get a discrete version, then you're not too far from the continuous version. Okay, there are plenty of details I'm missing, but that's kind of the idea. All right. Okay. So now I want to talk about. Here I consider n-1 cycles. Now I want to look at one cycle sweepouts. Okay. And so one way to do this is to, well, we can kind of use the same idea. So it's nice. I want to define look at one cycle sweepout. So there are several ways to define them. So one natural way would be just to consider a map from the manifold M to, let's say, Rn-1, okay, or more generally to n-1 complex, okay. And then we can define the width as before. I mean, really, what you do is you look at the pre-image and the H, then you take the volume of this level set. Oh, actually, well, it's not the volume. It's actually it's a length, because sort of you have to think about the fibers are as one-dimensional objects. So you look at the length, and then you take the supremum over all the fibers. and it's Rn minus 1 or this n minus 1 dimensional complex, and you take the infimum over all such mat F. Okay? And of course the question is, can you find an upper bound like that? Can you bound it from above in terms of the volume? And the right power this time is 1 over n. Okay? Well, in the two-dimensional case, it's true because of our result with Parent-Chef. It's true, though if you insist on having a constant that doesn't depend on the topology of M, it's false if you take R, and it may be true or not if you take P here. Okay, so I don't know. I don't know the answer. I have no idea. I mean, the problem is because, you know, with hypersurfaces, you know, you could decompose the manifold into two parts. Here, just looking at like actually n minus one, you know, an n minus one parameter family of one cycles. And it's a lot of too many parameters, and I really just don't know the answer to that question. But instead of considering, an n minus one parameter family of one cycles, okay, so here we have an n minus one parameter family of one cycles. Let's try just with just a one parameter family of one cycle. Okay, might be easier to handle, and also the infimum you would take, the width defined like that. I mean, I need to define, you know, what we mean here. But the width will be small than this one, so we'll have more chance of getting such a bound. Okay. All right. So the thing is that this one parameter family of one cycle. Okay. So here, okay, let me put it that way. This n minus one parameter of one cycle sort of sweep out the whole manifold. Okay. But now, if you consider only a one parameter family of one cycles, it's not going to sweep out the whole manifold if it's, you know, in higher dimension. Instead, it's going to. What you want is that this one parameter family of one cycle, you want it to sweep out. It's going to sweep out like sort of a two-dimensional homology class, okay, instead of the whole manifold. So here's how we can define such a sweep out. Just don't need this anymore. Okay. So in general, what you do, I mean, actually, you know, when you look at Birkhoff's process to to find a closed geodesic on the, say, on the two-sphere, what you do is, let's say I'm going to use this blackboard. All right. Yeah. So what you do is you have like sort of your round sphere. You have like a this slicing of the one sphere, just like that. And here you have just an arbitrary sphere, and then you take like a map of non-zero degree. You map this family to your in this sphere, so you get like something like that. And the point is that the curves you get, they don't necessarily slice the manifold. They're not necessarily disjoint. Okay, they're not level sets of anything. So you could have something like that. So here there's sort of intersection. You can kind of intersect other things, and you can even develop something where the curve is not simple anymore, and so on. Okay, so you can have something a little bit complicated. Okay, so it gives you more room. Okay, so here that's sort of the general results. Here you have this projection, and you see that the preimages, those level sets here, are loops. And then you map this one parameter family of loops to the two sphere. You use this min-max process, and you get a closed geodesic. A drawback is that it doesn't work for, it only works for spheres. So, it doesn't work when, let's say, the pipe, here, if you have like sort of an aspherical, like if you have a surface of higher genus, you can't apply this process like that, okay? Because there's no map of non-zero degree between the two sphere and your surface, in higher genus. Anyway, so one way to give you more room is to consider, say, like so you fix a surface, maybe even more general, like a two complex, and you map it to your manifold, and okay, so that's a map like that. And here on this surface, sort of, you have a slicing. Okay. And actually, to give you even more room, like previously, you just map. So that's the difference between taking map to R and taking maps to, say, a graph. Because if you take a map to R, just like that, the preimage here has two connected components. But if you look at maps to a graph, something like more like that, in this case, the preimage of this point is just this loop. All right? So that's your map H to a graph, gamma. Look at the preimage. Still get loops. And then, so you have like this one parameter family of loops, parameterized by gamma, by the graph. And then you map it to M. And of course you want this map to be non-trivial in some sense. You don't necessarily have some degree here, but what you want, for instance, is that this map is not homotopic to a map factoring through H. Okay, so you don't want this map to be homotopic to this one, where you get here the map H and there. Okay, so you don't want phi to be homotopic to such a map, right? So, for instance, that's the case. For instance, if the image of M, of the fundamental class of M, for instance, say you have a surface, like for instance, if this is non-zero, that's one way to ensure that you don't have, you can factorize your map like that up to homotop. Okay. So I think this notion of Sweepout has been introduced by Gromov. Okay. So, and again, once we have this, we can define the width. So previously, you one way to do it is, okay, so you have these pre-images. Look at the fibers of H. Then you map them to the surface. You take, okay, so that gives you a loop on your manifold. You look at the length. Then you take the supremum over all the loops, and then you take the infimum over everything else, over H and phi. Okay, so that's a notion of width for one parameter family of cycles. Okay, you need this, you need this homotopical condition because otherwise you would get zero. But here you can show that this is always positive. Okay, so when is that interesting? Here are some. Okay, here's the theorem. I'm not going to state the theorem in full generality. I'm just going to give you some examples. So say M. Okay, here's what I had in mind first. Is I wanted to look at the complex projective space. Because sort of inside CPN you have CP1, a two-dimensional sphere, and then you can ask yourself, what you want to do is to sweep out this two-sphere lying in the middle and compare that with the volume. Okay, it's only a one parameter family of cycles. And you want to do that. The problem here in this case, it's not a problem, but it's, first you can think of, okay, I have CP1 sitting inside, so the S2 sitting inside the CPN. So you have this S2 in CPN, and oh boy. Okay, to go a little bit faster. And one way to do that, what you can say is, okay, maybe if I can find a Lau bound for the minimal area of a sphere homotopic to CP1 that satisfies such an inequality. Okay, here that's the volume, that's the area, that's the volume of CPN. And here you want, that's dimension 2, that's dimension 2n. So you want to divide by this. So if you can assure that you always have this, then you can use the inequality, sweep out this sort of minimal S2 and get the inequality you want. Okay, so here should be 1/2, something like that. Okay. Unfortunately, this is wrong. Yeah, sorry. Yes, thank you. Okay, unfortunately, this doesn't work, but still, this is true, and that's the inequality I have here, is that you always have this inequality. N is the dimension of your manifold. It also works, like, say, give you some other examples, like on the torus, you have like two-dimensional homologic class, you want to split them by one parameter family of 1 cycles. Use this width, this notion of width, you always have this. And also on the sphere, on any surface, and here it doesn't depend on the genus, so it's something different from the result with Balashef, with Frank Balashef, where we had to have a constant depending on the genus, but here this notion of Sweepout is different. And also what you have is, if you're interested, you have this upper bound in terms of the diameter. Okay? So, all right. Okay. So let me give you like in 5 minutes just an idea of the proof. So actually, Rina, in a talk, introduced some of the techniques already, so that's going to help a little bit. So I'm going to just prove, not prove, but give an idea, the proof on surfaces, and just for this inequality here, because it's easier. So if you have so M is a surface, and so you take an epsilon-fine triangulation, and you argue by contradiction and assume that the width is greater than the diameter. Let's say, I don't know, probably I'm going to put this just to be, 10 times diameter. I don't know, something like that. And so the goal is, and then you consider an abstract cone. It's called Cm over M. Okay, so M here is now sitting in Cm. And the goal, as in Rena's talk, is to construct a retraction okay, and to get a contradiction. Okay, because we have a surface here, some sort of triangulation, and then you take a cone, and you want to retract the whole thing on the surface, and that's impossible, so that would be our contradiction. However, it won't work. Okay, so we have to be a little bit careful here. So. Let me do. So very quickly, so here we want to try to construct this retraction. Let's try. So first we have the identity map. Then you had this. You look at the vertex, and you map the vertex wherever you want. Okay. Wherever you want on the surface. Okay, you can do that. Now you look at the edges from this vertex. And then, so you know the image of the endpoints, and then you just join them with a segment. Okay. So this segment is of length at most two times the diameter. And then you look at the two-dimensional simplex from the vertex of the cone. And so this is the image is just it's kind of it's a geodesic triangle. Here it's epsilon, here it's diameter, that's the diameter. So the length is 2 times the diameter plus epsilon. And that should be less than the width I defined there. Okay? Because we assume that the width is much larger than the diameter. All right. So now you apply. Okay. So now you apply the curve shortening flow to those triangles. Okay. You apply the curve shortening flow to the triangles. So you have 2 cases. I mean, either it converges to a point, and then you can extend f to the 2 simplex, or it converges to a closed geodesic, possibly non-contractible. So there's no way you can extend f to the 2 simplex. However, what we can do is the following. We're going to consider a graph in the. Okay, so we have a 3-dimensional complex. It's the cone over the surface. And then we look at the one skeleton. So here we have this. So we look at the one skeleton. Dual to the one skeleton of the cone of your complex. That's called the complex P. Okay, so it's 3-dimensional complex. And inside, you do the following. You look at this graph. Okay, every time here, the curve shortening process converges to a point. You just look at this half edge. And when it doesn't converge to a point, that means that it converges to a closed geodesic, you take the whole edge. Okay, so you get something like that. Okay, so that's your graph gamma. And then what you know is that you can extend can stop here. So what you know is that you have this map F that's defined on the, okay, so it's defined actually, so if you remove this tubular neighborhood of gamma, you can slightly extend your map to P3, but not inside an epsilon tubular neighborhood of gamma. Okay. Because you have no abstraction for that. And what you see is if you look at the surface given by the boundary of this tubular neighborhood, so that's your map F. And you see that the pre-image, you have a map here from the surface. Okay, you look. You have a map from the surface to the graph, to the yellow graph, taking this slope, for instance, to this one, this point here to the end point, and so on. Okay, so what you see is that you have a map from the surface to gamma, to the graph. And by construction, the pre-images, that's H, are sent by F to loops of length, because you know everything, of length 3D plus epsilon or something like that. 3D plus epsilon or something like that. And so that's strictly less than the width. Okay? Which means that, and I'll stop there, if it's strictly smaller than the width, that means that this map is of degree 0. Therefore, you can extend it to some three-dimensional complex M with the same boundary as the boundary of the tubular neighborhood of the graph, and therefore what you get is a map not from P to your surface, but from a three-dimensional complex R with boundary M, with boundary M, and that's just impossible, because that would contradict the fact, that wouldn't give you a retraction from what I call P to M, but from another three-dimensional complex to M, and that's just impossible. Okay, so that gives you a contradiction. All right, I'm sorry, I had to go fast, and I'll stop here.